What we're going to be doing is making a video series about wireless link level simulation, specifically for wireless hardware design. In this video, I'm going to go over the clustered delay line channel developed by 3GPP, as I would say it is one of the most physically consistent channels between all of the different standardized channels in the Wi-Fi and cellular different like standards or whatever. And the reason for that is it's a geometry based stochastic channel. So what happens is there's a channel, there's a specific structure to it. And what happens is the different vendors like Nokia, Ericsson, and a bunch of different groups go out in the field, and in specific types of environments, they make measurements and they choose values for the parameters in this model so that it represents what the environment will bring. So I'll explain a little bit more later in the video, but why don't I share my screen to show you guys what I am talking about. Okay, so the 3GPP cluster delay line channel model. So first, I will focus on this channel model, right? So I'm going to focus on the line of sight component. So as you can see, this is assuming MIMO communication. So this will be the channel gain between the receive antenna U and transmit antenna S. And so what happens in a line of sight component, they call it line of sight, but yeah, so what happens is you'll obviously have one strong line of sight component and a non-line of sight aspect of that. So this will have much more power than the non-line of sight components, but you can't just because you have a line of sight, it doesn't mean that there won't be other non-line of sight components occurring. And then so in the wireless, I guess, research or academia field, we call this more of a Reichen channel, but going on. So I'll show what each of these terms are. So the line of sight component looks something like this, a lot of different parameters, a little intimidating, but I'll explain it in further detail in a sec. And this is what the non-line of sight component looks like. So similar structure, but there's a few differences. So first of all, again, I repeat myself, this is from transmit antenna S to receive antenna U. And for the line of sight, you have this one to represent that it's just going to be a single ray going from, the transmitter to the receiver. And this is what it looks like. For the non-line of sight component, however, it's broken down into clusters and rays within specific clusters. So this is a term in a double sum. So you'll have capital N rays and capital N clusters and capital M rays within a specific cluster, and then it will be a double sum, and each of the terms will look like this. So from both channels, on the left-hand side, you'll have a receive embedded antenna element pattern broken down into its theta and phi polarization directions. You can import this from maybe some simulation tool like HFSS or from measurements that you've made. On the right-hand side, it's the same thing but except for the transmitter side. So you can see it's basically the same idea for that, right? In the middle, for both of these, you have what we call a polarization matrix. And the terms are a little bit different, but that's because of the structure of the line of sight and non-line of sight components. So for the line of sight, you'll have a specific ray going from the transmitter to the receiver. And so in that case, since the ray will not hit any objects on its way, the polarization will not get distorted. So it will the theta component from the transmit side will transfer to the theta component on the receive side. The phi component on the transmit side will convert to the phi component on the receive side. This -1 is due to the way the coordinate system is set up, but what's important is that this matrix is composed of just zeros and ones. In the non-line of sight component, however, one of these rays, what will happen is it will bounce off different objects before eventually hitting the receiver. Now, every time a ray hits an object, its polarization will get distorted, and there will be a phase that will added due to its interaction with the object. If you know what the object is, you know the different material parameters, you can actually physically model this. But what 3GPP does is it tries to model all of these effects together because it's multiple objects hitting it, and it does so statistically. So what it will do is there's going to be an overall phase that this specific array going around will get, and it will be represented by these exponentials, right? And the phase, this theta, this phi-ish looking component, it will be generated from a uniform distribution. So it's random. There's going to be this kappa, which we have, which is the cross polarization ratio, which tells you the ratio between the co-polarized component and the cross polarized component. And so it kind of gives you an idea of how much of the cross polarization power gets converted into how much the polarizations get distorted. But again, another thing to mention is that this thing is modeled statistically to represent all of the aspects of the different bounces in the environment. It follows a log normal distribution. That being said, you have the phase delay of the travel and all of the different like object interactions by this exponential, like the propagation delay. But in the line of sight component, it will just be one overall propagation delay from the transmit receive side and the distances of how far they are from each other. The other exponentials are due to the antenna array phase offset. So the different antenna elements when a signal hits an antenna array, the different antenna elements are spaced differently from one another, and so they will receive the signal at a different time, and then um, this will be represented by this exponential. So this is for the receive array, an element in the receive array, and this is for the transmit array, and then you see it's the same thing here. And finally, you're going to have one final term on both sides for the Doppler. So if you have a moving object, there's going to be some phase offset due to the Doppler shift. On the non-line of sight component, you have this factor here, and this Pn is the power for that cluster, and it's going to be divided by the m total rays that we have. It's obviously square roots because this is a power, and this is a channel that we're looking at. So yeah, so what happens in an environment, or like in what 3GPP tries to do, is that depending on the different a specific scenario you're in, like maybe urban, rural, suburban, you have a different set of values for the parameters that we input into this model. So the different angular spreads, the different means of where the clusters are coming from and everything like that. And these are based off measurements that have been done. And so what this entire model does is, again, like with a finite set of parameters, it tries to model the interaction that goes on, and it does a relatively good job. But I think the point that we are trying to make is that when you're specifically looking at things for doing detailed hardware analysis, maybe there's some limitations of this channel model. And we're going to make a few follow-up videos to talk about that. Thank you.